Okay, in this video we're going to talk about action potentials. Now remember, action potentials are the principal way that neurons send signals long distance and really rapidly. So when we talk about neuronal communication, it involves action potentials. These occur only briefly within muscles and axons of neurons, and what we find is actually the action potential itself is a brief and rapid change in membrane voltage that could be as great as 100 millivolts difference. So action potentials differ than graded potentials because they don't decay over time and distance. Rather, these action potentials are regenerated as they move, so that's why they maintain the same size and shape as they travel. Now in neurons, they refer to these as nerve impulses, and the action potential itself is due to a change in current, which changes the voltage, and the channels that open that can change your current are the specific voltage-gated channels. Now, at a resting state, all of our voltage-gated channels are closed. So the voltage-gated sodium channels are closed, voltage-gated potassium channels are also closed. So the only ones that are open are the leakage channels. Remember, we have sodium leak and a potassium leak. And potassium leakage is far more leaky than sodium. So we talked about how because potassium flows out of the cell due to its electrochemical gradient, how that makes the inside of the cell slightly more negative. And this is actually what maintains the resting membrane potential. Now, each sodium channel, voltage-gated channel rather, has activation gates and an inactivation gate. The activation gates are closed at rest but open with depolarization, which allows for sodium to flow. And then the inactivation gates are open at rest but then block the channel once it's open to prevent additional sodium from entering. So think of the activation gates as basically allowing sodium to flow, and then the inactivation gates stop that sodium. So what we find then here, some of the key players in the action potential are the voltage-gated sodium channels and the voltage-gated potassium channels. For the voltage-gated sodium channel, it's closed at rest, right? We're saying that you find a lot of sodium outside the cell. The inside of the cell has less sodium, so sodium wants to flow down its diffusion gradient into the cell. However, because this channel is blocked by the activation gate, sodium can't flow. But if there's enough depolarization, these activation gates can swing open and allow for sodium to rush into the cell. So that as sodium rushes in, it causes further depolarization. But after a certain amount of time, the inactivation gates block that channel and they prevent further sodium from rushing in. So what we find is that the activation gates open due to a change in voltage at a sufficient amount of depolarization, and the inactivation gates close due to time. So they actually close pretty soon after they open, but these actually get reset later on. Now, the voltage-gated potassium channels are closed at a resting state, and they open at a very depolarized voltage. Once they open, it allows for sodium to flow out. Potassium rather. So potassium flows out of the cell into the extracellular fluid down its electrochemical gradient, which makes the inside of the cell more negative because you're removing positive charge. Now, eventually, these voltage-gated potassium channels also closed at a certain voltage. So each potassium channel has one voltage-sensitive gate. It's closed at rest and opens slowly with depolarization. So if we zoom in on these voltage-gated sodium channels, remember we have an activation gate and an inactivation gate. Remember, the activation gates are closed at rest while the inactivation gate is open. However, the activation gates still block this channel. If there's enough depolarization, sodium flows in and depolarizes the inside of the cell. But after a certain amount of time, the inactivation gate closes this channel and prevents further sodium from rushing in. Now, at a certain voltage, these activation gates reset, and the inactivation gate also resets. Now, in terms of the events of the action potential, we find that at rest, only the leakage channels are open here. So that because of potassium leakage, the voltage is fairly negative because potassium is leaving the cell through that leakage channel. But if there's enough depolarizing stimulus, these voltage-gated sodium channels swing open. And so we call this the depolarization phase of the action potential. So when these voltage-gated sodium channels open, this depolarization allows for sodium to rush into the cell. Sodium activation gates open, and sodium influx causes even more depolarization, which causes the voltage to go from like negative 55 all the way up to positive 30 millivolts, because as sodium rushes into the cell, it's bringing in more positive charge. So that's what we're seeing here, is that the rising phase of the action potential is due to positively charged sodium rushing into the cell. Sodium's able to flow through this voltage-gated channel now because these activation gates have opened. And because they're open, now the channel's open, and allows sodium to run down its electrochemical gradient. Now, eventually, this inactivation gate is going to close, and it closes due to a time-dependent manner. And so once these inactivation gates close, near the peak of the action potential, it prevents further depolarization, so it determines the peak here. So it can't just depolarize forever and get positive forever. So right around that peak of the action potential, this is where the repolarization phase occurs. This is when the voltage-gated sodium channels start inactivating due to those inactivation gates, and right around the same time, the voltage-gated potassium channels open. So sodium channel inactivation gates close, membrane permeability to sodium declines, so the action potential stops rising in terms of voltage because you're preventing sodium from rushing into the cell here. Right around the same time, voltage-gated potassium channels start to open due to their voltage that they open at. And so what we find is that they allow for potassium to now flow out of the cell. And because you're having potassium exit down its electrochemical gradient, it causes repolarization, which is when the membrane returns back to a resting voltage. So think of repolarization as basically when voltage starts to get more negative back towards resting membrane voltage. And so what we find is that the falling phase, or the repolarization phase of their action potential here, represents an efflux of potassium out of the cell. And because you're removing positive charge, it makes our voltage more negative back down towards a resting state. However, what happens is that because so many voltage-gated potassium channels open here, some potassium channels remain open, allowing excessive potassium efflux. And that because of excessive potassium loss, we get basically a membrane voltage that becomes even more negative than its resting state. And what we call this is hyperpolarization. So hyperpolarization is when the membrane dips below resting voltage, but this is what resets the voltage-gated sodium channels back into their resting state. So that way they actually can be able to be activated again. So hyperpolarization is when voltage of your neuron here is even more negative than rest. This is because so much potassium is left, it's actually made the inside of the cell even more negative than a resting voltage. So in terms of the events of the action potential, we have rest, which is due to leakage channels. We have the rising phase or depolarization phase, which is due to the opening of voltage-gated sodium channels. Once those activation gates open, sodium can actually rush in, causing depolarization to occur. And then near the peak of the action potential, the inactivation gate of your voltage-gated sodium channel closes right around the same time that the activation gates of your voltage-gated potassium channels open, which allows for potassium now to exit the cell. But because you're removing positively charged potassium out of the cell, it makes our voltage negative back down towards rest. But because so much potassium flowed out of the cell, there's a phase here called hyperpolarization, which is essentially when the inside of the cell becomes slightly more negative than the rest. And this is important because first of all, it helps to reset the voltage-gated sodium channels because the inactivation gate actually opens again, which then allows for our voltage-gated sodium channels to be stimulated once more. Now, eventually these voltage-gated potassium channels will close near the end of hyperpolarization. And at that point, resting membrane voltage will slowly go back down towards, its negative 70 millivolts or so, away from hyperpolarization. And around this time, the voltage-gated sodium channels are ready to be activated again, and you can generate another action potential. So what we find then is that repolarization resets electrical conditions, but not the ionic conditions. So in order to reestablish these concentrations, sodium-potassium pumps are working in overtime. In fact, they're always pumping sodium and potassium, even during the action potential. And their function here is to not really contribute to the action potential directly, but rather the sodium-potassium pumps maintain the concentration gradient that allows for the action potential to occur. If we didn't have a gradient of more sodium outside the cell and less inside the cell, then you wouldn't get the rising phase of the action potential because sodium wouldn't flow. Same with potassium. If you didn't have potassium in excess concentration within the cell, it wouldn't want to flow out. So we need these concentration gradients in order for action potentials to occur. But what's also important to note is that each action potential doesn't allow for so many ions to flow that it changes the concentration gradient significantly. In fact, it would take hundreds, if not thousands, of action potentials before you ever affected concentration significantly. So that each individual action potential doesn't change the concentration gradient, it just changes the voltage. But over time, we need these sodium-potassium pumps to maintain those gradients. So remember how they work is they use the chemical energy in ATP to basically pump sodium out of the cell, which is why it's in higher concentration outside the cell than it is in, and simultaneously pumping potassium in, which is what makes potassium in higher concentration within the cell.